Hey guys, in this video I'm going to give you the general setup for a strict sequencing game. This game is from the June 2007 LSAT. It's the third logic game. So in this game we have 7 week-long voyages occurring in the first 7 weeks of a season, weeks 1 through 7. So this right away tells us that we're dealing with a game that has some kind of sequencing component, and because we have only 4 different destinations, and some of these destinations will repeat, that suggests to us that this is more likely to be a strict sequencing game than a relative sequencing game because of that repetition. We don't typically see repetition of variables in relative sequencing games. Additionally, when we move on to the rules, we see that the rules are referring to specific weeks of the voyage rather than simply relating the variables to each other in a before and after fashion. So I set up 7 different spaces here numbered 1 through 7, 1 for each of the weeks, and I've laid out some rules which I'm going to explain. We know that J is not going to be the destination in week 4, so I put J with a slash through it under the 4th week. We know that T will go on week 7, so I put that down on the 7th space. We know we're going to have 2 voyages to M and at least 1 voyage to G in between those. So I put down M space G space M, loosely relating those different variables to each other. They tell us that whenever we have a Jamaica voyage, we will have a Guadeloupe voyage in the week immediately preceding. So that tells us that whenever we have J, we're going to have GJ occurring consecutively in that order. This is a conditional statement, although it's worded a little bit in a confusing manner at first. Look at the word any in this rule. G will go in the week preceding any voyage it makes to Jamaica. So the word any is a sufficient condition indicator. So anytime we have J, we have G going prior. So if we have J, then we have G going prior. So J requires JG occurring consecutively. This does not mean that whenever we have G, we're going to have J. It means that whenever we have J, we're going to have G. So G can occur independently of J. It's just that J cannot occur independently of G. And finally, we never have the same destination going on consecutive weeks, so I just represent that ambiguous destination with an X. So no two variables, none of the same variable occurring consecutively. So if we have T on 7, as we must, we know that we cannot have T going on 6. There's a very small inference there. What other inferences can we make here? We know that this particular rule with J and G is kind of powerful. You know, J can't go on 4, but that doesn't mean G couldn't go on 3. Again, like I said, G can occur independently of J, so G being on 3 would be perfectly fine. What we can infer, though, is that J can never be on 1. Because if J were on 1, how could we have G occurring immediately before it? It simply would not fit. There's no way to make that happen because there is no week prior to week number 1. That's the first week of the voyage here. So J can never go on 1, period. And this right here serves as our general initial setup for the game. Of course, we'll be doing a lot more work over the course of the game as we get into specific questions. Now that we've done the initial setup here, let's take a look at the questions. The first question for this game is a typical orientation question where we're simply going to want to take one rule or inference at a time and apply that rule or inference to all 5 answer choices looking for violations. So one thing we can do is take the inference that J can never be on 1, scanning through all choices looking for violations of that. And we see that choice C has J on 1. That's unacceptable, so we can eliminate C off the bat. Next, we could take the rule that T has to go on 7. Any choice where T is not on 7 could automatically be eliminated, so we can get rid of E, since E has M on 7. Next, we can use the rule that J can never be on 4. Checking for violations of that, we see that choice D violates this, having J on 4. So now we're down to only A and B. And let's think about what rule we haven't really used yet. We haven't used the rule that we have to have M before G before M. Exactly, we have to have a G in between the 2 M's. So looking at the remaining choices, choice B violates this, having only T in between the two M's and not having G between them at all. So B is gone, leaving A as our answer for number 11. Next, number 12, what cannot be true about the schedule? So what would be unacceptable for any valid scenario? Let's simply run through the choices. T going on 6, we know from our initial inference here that T cannot go on 6 because of the rule that no destination occurs on consecutive weeks. So A is our answer off the bat for number 12. We'll take a quick look at the other choices though. M on 5, no particular reason to believe that couldn't happen. J on 6, that wouldn't violate anything. J on 3 seems fine. And G on 3 seems fine as well. None of those other choices stand out as being problematic in any way. So A is good. It's our answer for 12. Next, number 13. If we had T on week 5, what could be true? So let's put T onto week 5 and see what inferences result. So right away I start off by making a new diagram, keeping the main diagram clean of course, and drawing a new one where we stick T on 5. So if we had T on 5, we know that we wouldn't be able to have J on 6, since J would require G to come immediately before it, and there wouldn't be any room for that if we have T on 5, of course. So J cannot be on 6 in this scenario. So J can't be on any of 1, 4, or 6, and of course J can't be on 5 or 7 because T's on those spaces, so that leaves J to only be on either space 2 or space 3. So I'm going to make two different main diagrams here, one where we put J on 2 and one where we put J on 3. So here's J on 3, and then I'll stack the J on 2 possibility above that, keeping T on 5 and 7 as constants, of course. Whenever we have J, we have G occurring immediately before it, so when J is on 3, G is on 2, and when J is on 2, G is on 1. Now, of course, we have to have M before G before M, so in the top possibility here, that means M is going to go on 3, G is going to go on 4, and M is going to go on 6. So we have GJM, GT, MT. In the bottom possibility, we know that whatever happens, we're going to have an M on 1, since if we put both of our M's on 4 and 6, we wouldn't be able to fit a G in between them. So on the spaces 4 and 6 remaining, we basically have M and G interchangeable, since we can't have J on those spaces, and we can't have T on those spaces since T is already on 5. So we simply have M/G on 4 and G/M on 6. Now let's run through our answer choices using these two diagrams to see what results. So could we have T on 1? Of course not. That's not happening in either of these scenarios, so A is gone. Could we have M on 2? No, we have either J or G on 2, so B is gone. Looking at C, G on 3, no, we have M or J there, so C is gone. M on 4, yes, that could happen in the bottom possibility because we have M/G there, so D works and it's our answer. We'll take a quick look at E though. J on 6, no, J could not possibly be on 6 here, which we inferred off the bat, since we know that T on 5 would block G from resulting, going immediately before J if J were to be on 6, so E is gone, leaving D. Next, number 14. If we had G on 1 and J on 5, what must be true? So of course, let's just draw a new diagram, keeping the main diagram clean, putting those on it and see what happens as a result. We have G on 1 and we have J on 5. Now of course, J on 5 requires G to go immediately before it. And now what can we do? Well, we have the MGM rule to deal with. We know that we can't put both of the M's on 2 and 3, since of course that would violate this. So one of those M's will have to go on 6, and then we're going to have an M on either 2 or 3. We don't know which one, of course. It's still a little bit ambiguous there, but at least we're able to fill in the other spaces. And what we have here will likely be enough to solve the question. So they're asking us what must be true. So our answer is not going to be about weeks 2 or 3, since there isn't really a must about that. Our must is going to be something in one of the concrete spaces here. So let's scan through the choices, ignoring A, B, and C for a moment, since they mention weeks 2 and 3. Looking at D, G on 6, no, of course, that isn't even possible. We're going to have M on 6. So for that reason, D is gone. And then looking at E, M on 6, yes, we do have that as a concrete inference, something that must be the case. So E is our answer for number 14. Next, number 15, if we had G on 1 and T on 2, what must be true? So again, new diagram specific for this question, G on 1 and t on 2. What must be true? So things might seem a little bit open-ended here, and they are at first glance. But if you think about this MGM rule, it actually firms things up quite a bit. We know we have to have MG and M going at some point on 3, 4, 5, and 6, and we also have to use J at least once, since we have to include all 4 of G, J, M, and T in any valid scenario. So where's J going to go? It can't go on 4. Certainly can't go on 3, because then how could we comply with the GJ portion of that rule since T is on 2? So J can't be on 3 or 4. J certainly cannot be on 6, because if J was on 6, we'd have to have G on 5, and then we'd have the M's touching on 3 and 4, which is unacceptable. So J cannot be on 6 either. J can only be on 5. If J is on 5, G is on 4, and then we have to have the M's going on both sides of G, not necessarily consecutively, of course, but before and after it. So M's going to be on both 3 and 6. So now they're asking us what must be true. Must M be on 3? Yes, we have that here, so we're good for number 15. I'll take a quick look through the others, though, although it's pretty clear that A is the answer. M on 4 does not happen. G's there, so that's gone. M on 5, no J is there, so that's gone. G on 3, no M is there. And G on 5, no J is there, so A is our answer for 15. Next, number 16. If we had M on week 3, then what could be an accurate list of what's going on 4 and 5, respectively, in that order? So let's put down M on 3 and see what we can infer off the bat here. Well, of course, J is never on 4, so right away we can get rid of choice B. Let's see what else we can infer. We cannot have M on 4, since we can never have the same variable going consecutively, so M cannot be on 4. That gets rid of choice C off the bat as well. Since those were like the two easiest to knock out, let's now simply run through the remaining answer choices. Looking at A, G, and T on 4 and 5, that seems perfectly fine, doesn't really cause any problems, so let's just leave that one alone for now and hope to eliminate D and E. Looking at D, T and J on 4 and 5 might seem fine at first glance, but then we have the rule that J requires GJ consecutively, so D is actually violating that rule and is unacceptable, so D is gone. Then looking at E, T and M violates the MGM rule, since we only have 2 M's in the game and we have to have a G in between those at some point. So E is gone as well, leaving A for number 16. Finally, number 17, general must be true question. This question has the potential to be very time-consuming because there's a lot of things that we would have to disprove if we wanted to solve this question simply by process of elimination. But one thing we can do is look back at previous valid scenarios in the hopes of at least eliminating a choice or two. So keep track of all the previous work that we've done so far and look back at it now. Looking at choice A, G in either week 1 or week 2, must that be the case, or have we ever had a valid scenario where we did not have G in at least one of those 2 weeks? Looking back, we've always seen it thus far. Doesn't mean that it has to be the case, but means that we should leave it alone for now and hope to eliminate something else. Looking at B, M in either week 2 or week 3. We actually saw back in question number 13 that we could have M on 1 and then have M again in either 4 or 6. So we didn't have to have M in either week 2 or week 3, so we can eliminate choice B. Looking at C, at most 2 G's. We've never had more than that, doesn't mean it's not possible. Skip that one for now. D, at most 2 voyages to J. This one should stand out a little bit because J is a particularly limited variable. We know that whenever we have J, we have to have G immediately before it. So if you think about the number of variables that we have in this game, we've already got to use all 4 of G, J, M, and T. We know we're going to have 2 M's because of the MGM rule, and we know they tell us that M goes exactly twice. Then if we had more than 2 J's, meaning we already have a J here and we actually have 2 more, so 3 J's altogether, that would already lead us to have 7 variables for our 7 spaces. But additionally, whenever we have a J, we have to have G immediately before it. So whatever our number of J's is, we have to have at least that number of G's as well. So if we have 3 J's here, we have to have at least 3 G's. we already have 1 G is given, so we're going to have to add on 2 more to our total. And as you see now, we already have 9 variables that we would have to have in order to have more than 2 J's. But having at least 9 variables for only 7 spaces would not work, since we can only have 1 variable per space in this game. So having more than 2 J's is impossible, meaning that our maximum number of possible J's is only 2. So for that reason, D is our answer to number 17. And then looking at E, just to be thorough here, at most 2 voyages to T. Well, T is a pretty open-ended variable. There aren't really a whole lot of rules about it, so there's no reason to think that we couldn't have 3 T's perhaps. But since we've proven that D is impossible, it's impossible to have more than 2 J's, D is a must, and therefore is our answer to number 17.